This might be the most important reinforcement learning algorithm in the whole AI, proximal policy optimization. And once you understand this, you will easily be able to understand every other. This is not only used very frequently in a lot of different LLMs, reasoning, and all other reinforcement learning tasks, like robotics as well, but all of the other algorithms from LLM, reasoning, robotics, etc. are derived from these, are very similar to proximal policy optimization. So anybody who wants to learn reinforcement learning, LLM reasoning, etc. needs to master this. And we will talk about this in the context of large language model, but it's same intuition for every other task, robotics, everything. You will understand the importance ratio, advantage, minimum, maximum, clipping, everything that will be very intuitively explained on why it happens, not just how it happens, and why we do these things that we do. Let's first take a look at on-policy training. Let's say you ask the LLM what the capital of France is, and it generates answer that it's Paris. So now you want to reward LLM with +1 reward because it got the correct answer. So what this does, rewarding, is it will change internal weights of the model of the neural network so that Paris becomes even more likely next time. It generates, so this is classic gradient descent, gradient updates, this classic backpropagation, how neural network works. So this method is actually good, but it's slow and expensive compared to off policy, because here we generate sample once, we reward or not reward the model based on that sample if it's correct or wrong, and then we generate the next sample. Now off policy will actually reuse this same sample multiple times to teach the model. So that was on policy, but let's now look at off policy of how it reuses same example to teach the model many times. Here we will also generate an answer to this question, Paris. But we will also look at what the probabilities are for different tokens. For example, if this model is not so good in the beginning, then let's say it can give 10% chance for the token Paris, but it can give 8% chance and 15% chance, for example, for some other tokens. But let's say it randomly picked Paris as the correct answer. And we will reward it, so we will now make the weights of the model be more likely to output Paris next time, because it got a positive reward for the Paris. But this is important. We are actually not updating the weights of the model that generated this word, Paris. We are updating a separate model weights. So it's like in the beginning, that new model is a copy of this old model, so they are same. But this old model generated the Paris, but then we are using the new model. We are updating the new model a few times with this output. And I will explain why. So after we judge that this first time the Paris was correct, so the old model generated correctly word Paris, we will now reward the new model. We will change the new model, not the old model. We will change the new model, which is in the beginning same as old model, but now it will get actually changed, rewarded, so now it will become more likely to generate word Paris. And so next time, we will also look at the word Paris probability, and now it will be 40% because now it's smarter, the new model is now smarter. So it's important that we don't actually generate the answer again. We don't prompt the new model to generate answer again, or any model, or old or new. We just look at what the probability of the word Paris happening again in the new model is. So this is a lot faster and easier. Just check the probability and you don't need to generate it again. So now the probability of Paris is gonna be higher because we rewarded it, we made it higher in the new model. And so we're gonna calculate this importance weight or importance ratio, which is just the probability of the new model generating Paris versus the old model generating Paris. So if in this case it will be 40% or 0.4 over 10% or 0.1. So the new model is 4 times more likely to generate word Paris, which we can look at this as it learned that the Paris is a good answer here. Now that we understand that, let's check different example. To calculate reward for this example, for one example, we need to also look at other examples to understand the overall ability of the model. If the model is bad, then we don't want to actually punish it too much for getting wrong answer, because it will not help in the training if we just punish it all the time. So if the model is bad, and if it gives a correct answer, then we want to reward it a lot. But if it's good, but it gives a bad answer, then we also want to punish it a lot to remove all of the final bad answers. So basically, if it's bad, we don't want to punish too much. If it's good, we don't want to reward too much. But we will see this better on an example. So first question is, what is the capital of France? The capital is Paris, so this answer is correct. And the second, what is the capital of Germany? The capital is France. This answer is wrong. And let's see how this works now. In this case, our reward function will give +1 if the answer is correct and -1 if the answer is wrong. So as I said, we will have to compare the answer to other answers to know how good model generally is. Like, is it doing much better than average, or much worse than average, or a bit better, a bit worse? And that's gonna influence our reward. Because if it's very good, we don't want to reward it a lot for a good answer, because it already has good weights. It's a good model. So if we give it also big reward for good answers, we can then ruin other weights. But if it's bad and gets a lot of wrong answers, and now suddenly one good answer, then we want to reward it a lot to push in that direction more. For that, we will use advantage. Advantage tells us how much better or worse this particular answer is than the average answer or the expectation. So to calculate advantage, we're gonna say actual reward that it got minus expected reward. So expected reward is similar to like average reward that it would get. So you will notice that if the expected reward is very low, then advantage will be high. If this actual reward is high, then we will subtract a small number. But if expected reward is high and the answer is also correct, then advantage will be low. This works well with what I just explained. Now, how is this expected reward calculated, for example, for this question, the capital of France? This is actually quite a complex process. There are different ways, different methods, so it would take me maybe 10 to 15 minutes at least. It's a separate whole video. There are nuances and details. So I'm not going to do it in this video, but I can shortly summarize two methods. One method would be to just generate a bunch of answers to this same prompt. Just ask it over and over again, the same question, and see which ones are correct, which ones are not correct. And then there is some formula or different even ways there to calculate expected reward by looking at how the model answers this question over and over again. Or you can also have another neural network that learns to generate expected reward. That's another way as well, based on this question or other questions in the past. So there are different ways to do it. And each has advantages and disadvantages, but I would leave it for a different whole video. It's complex. So now that we have expected rewards, let's calculate the actual advantage. So the actual reward we got for Paris is +1 minus expected reward 0.6. So the advantage is 0.4. So this is how much better than expected it performed. And here it actually performed worse than expected. For example, here it was expected to perform well. 0.5 is expected reward. But it got -1. So it performed actually way worse than expected. So now the advantage is -1.5. This is a big disadvantage, or let's say this is a big negative advantage, because it was expected to do well actually. Just by looking here, This would tell me that in this example, model is actually quite good because the expected reward is positive and it's quite big. So as I said, if its model is quite good, we don't want to change weights too much if it also generates correct answer, which it did here. But if it generates a negative answer, then we want to punish it more because it's already good, so we want to punish it more to remove even those last imperfections as much as we can. And finally, we get to the last formula, which is actually a lot easier than it seems. So the purpose of this, if this gives a positive number, it means the answer is good, and we want the weights of the neural network to be updated to make this answer more likely. And if this is negative number, we want the answer to be less likely because it's a wrong answer. But this is calculated for every single token. So different tokens will be differently more likely or less likely. However, if the answer is correct, every token in that answer will become more likely in the model from that point on. If the answer is incorrect, every token will become less likely. Now, how much more likely? It depends on this importance ratio that I will repeat what it is. We calculated that. So it depends on how likely, if it was very unlikely previously, but now it gave correct answer, then it will become a lot more likely. But if it was very likely previously as well, and now it got correct answer, then its likeliness will not change so much. So I'm gonna explain this again. But before I summarize importance ratio again, I will say that advantage number is same for every token in the entire sequence. So advantage depends on how much this entire answer, or how much the answer was better than the expected answer. So it's same for the entire answer, entire sequence, same number. But the importance ratio is actually different for every token. It's like how much this token the model thought was likely before. Let's check importance ratio for our two new examples, France and Germany. So the answer to capital of France was correct by the model. It was Paris. And so imagine that we actually asked it, first time we asked it, it thought that Paris was 30% likely to be the next token there. And so the answer was correct, so we updated the new model. And the second time we asked it the same question, it thought the Paris was now 60% likely because now it learned that Paris is correct answer. It was there, so it got a reward. So now it updated weights, and the second time we asked the same question, we checked that actually now it thinks Paris is even likelier, 60%. So that's gonna give us importance ratio, the new likeliness over the old likeliness. So it's 2. So now this is the weight. Now this weight, importance ratio or important weight, will actually strengthen the correct advantage. You'll see later that this is multiplied with the advantage. So if the model is performing better than expected, so it has positive advantage performing better than expected, then it will actually tell it continue strengthening this Paris token, continue increasing its probability because it's making the model perform better than expected. But if the model has negative advantage, if it performed worse than expected, then that negative advantage will get amplified by 2 here. So the reward will actually be negative, it will be punishment. So if the model performed worse than expected by strengthening this probability of Paris, then it will be punished even more the more it strengthens probability of the Paris. It will be punished more. So this will multiply the punishment, the negative advantage. And remember, we just generated the answers to these questions once in the old model. And now we are every time just checking the probabilities of those tokens with the new updated models. So what should happen in theory is that because this was correct answer, its probability should rise. So it is rising. So now it's 60%, it was 30%. So while we are updating this new model, it should rise, okay? But this was the wrong answer. It said that capital of Germany is France. So we would expect with the training the probability of this token France to fall because it's wrong. And that's exactly what's happening here. First, the probability was 20%. And maybe it got unlucky, so it picked this word. But after we adjusted parameters, maybe once or even a couple of times, it doesn't matter, we see that now probability is just 1%. So now it's learning that it shouldn't be France as the capital of Germany. So now importance ratio is 0.05. Now this is gonna be interesting. So it has a few moving parts here for you to understand. So we see that now importance weight or importance ratio is very small. The model is already expected to do poorly on this question because it gave like wrong answers before, let's say. So the advantage will actually be a small negative number. If it gives wrong answer, I should say, let's say it gives wrong answer here again. The advantage will be small negative number because it was already expected to do poorly. The expected reward was very low. So we have a small negative number multiplied by this small importance weight, so we will just get a small punishment if the answer is again wrong. Because as I said, there is no point in punishing model if it's bad. So then you want to reward a few correct answers. A lot more. But if it gives correct answer here, then as I said, importance weight will remain the same. It will be this whether or not it gives correct or wrong answer in the next try. But if it gives correct answer, then the advantage will be very big positive number compared to other, like maybe 1 or up to 2 or something like that. Because it's expected to do poorly. And if it gets a correct answer, then the advantage, the way it's calculated, it will be huge advantage because it's expected to do poorly. So when we multiply that big number with this importance weight, even though it will shrink it quite a bit, it's still gonna be higher reward than the punishment if the answer was wrong. It's all because of the advantage, because it's expected to do poorly. So the reward will be higher than the punishment if it's wrong. So let's look at this formula again. We just have importance ratio times the advantage that I just explained. And this is calculated for every single token. And so what it will do on the whole is the following. If the model is expected to perform poorly on a question, but gives correct answer, then it will get big reward. But if it's expected to perform poorly and gets wrong answer, it will get small punishment. But also, if it gives correct reward with some token, but that token was very unlikely before, but now it gave correct reward, then the probability of that particular token will increase a lot because it was very unlikely before, but now it gave a correct answer. And actually you can reverse all of this logic for the negative answers. If it was very likely but gave negative answer, then the likeliness will go down a lot. But if the token was unlikely in the first place and gave negative answer, it will not go down so much in the likeliness. So now that we understand this part, let's see. This part is actually almost same. You see, you have times advantage. You are just clipping this importance ratio between 0.8 and 1.2 because we'll explain why, but here epsilon is usually 0.2. So this range will be 1 minus 0.2 and this will be 1 plus 0.2. So you are clipping. If importance ratio gets lower than 0.8, then you will make it 0.8. If it gets higher than 1.2, you'll make it 1.2. And we will explain why. But I just first want to explain that. So, and then we take minimum between this. So there are like four possible cases here. Like there are two moving parts, the minimum between these and the importance ratio clipping. So importance ratio is always a positive number. It's just new probability divided with the old probability. It's always a positive number. And in this term, it will not be clipped. In this term, it will be clipped between these two values. So let's see how these two terms interact with the minimum for different types of situation. The first case, advantage is higher than 0. So it means that model performed better than expected. So it gave a positive, correct answer in this case. The goal here is to make the likeliness, the probability of all of these tokens increase. So they're even more likely to give positive answer, correct answer next time. Now, if for this particular token, whichever token we are looking at currently, the importance ratio is between 0.8 and 1.2, which means that the new model made this token just a bit more likely or a bit less likely than the old model. As importance ratio of 1 would be exact same likeliness of this token happening in the old model and the new model. So if the importance ratio is between 0.8 and 1.2, then this clipping will give the same result as not clipping. So both of these will have exact same result because there is no need to clip. So then our reward will just be the advantage, which is a positive number, times importance ratio, which is also some positive number in this range. So that's our reward. Now we will make all of these tokens more likely to happen. But if the importance ratio is above 1.2, for example 2, which means the new model thinks this particular token is 2 times more or gives it 2 times higher probability to generate. And at the same time, the answer was correct. We don't want to actually increase the probability of this particular token that has this importance ratio too much anymore, because the answer was correct and it already has a decent increase in probability compared to the previous old model. So we don't want to increase recklessly because we don't know what's going to happen. It can actually mess up other things. That's what happens in neural network. So then the importance ratio of 2 will get clipped to 1.2 because this is the maximum amount we want to actually increase the probability. We don't want to increase it by the whole 2 times. We don't want to reward it this much. So we will just take the minimum. We will get this minimum reward, a smaller reward, because we don't want to increase too much. We want to clip it. If the importance ratio is below 0.8, for example 0.5, which means that the new model made this token less likely in comparison to the old model. But choosing this model gave the correct answer. Choosing this token gave the correct answer. It's positive advantage. We want to allow it to give as big of a reward as it wants. We don't want to restrict the reward because we accidentally made a good token less likely. So we want to let it increase the likeliness or give her as big of a reward as it wants. So we don't want to clip. And Gemini's explanation is not actually that good here. It's a bit confusing. Just understand that we don't want to constrain this case. We want the model to fix its mistake of accidentally making good token less likely in previous iterations. And it's not gonna be a huge reward anyways, because the advantage is smaller than 1. So it's not gonna be a huge reward anyways. Now let's see if the advantage is negative, which means that it gave wrong answer. Regardless of the value of this advantage, the value is more dependent on the expected answers, expected reward, expected correctness. But if the answer is wrong, it will always be a negative number here. It will always be worse than expected, because expected will be somewhere between how many positive, how many negatives. So that's why if the answer is wrong, this will always be negative number in the advantage. And Gemini is kind of weird. Don't read this. What is this? And then there is a bit of an issue here. If the advantage is lower than 0, then we will use max, not min, in standard proximal policy optimization. In case of importance ratio being between 0.8 and 1.1, then it will not get clipped. So this term will be same as this term, so it will just get calculated. If the importance ratio is less than 0.8 and the advantage, the answer was wrong, intuitively that means that we successfully made the wrong token less likely. So now we made the wrong token that shouldn't be there less likely, so we don't actually want to make it even less likely. We don't want that. We don't want to continue pushing here. It's already less likely. Now we are kind of satisfied. We want to make it also a bit less likely, but not too much less likely, because that could cause other problems. Just like making good tokens very too much, even more likely. So now this first part will be, let's say advantage is -1. So we multiply importance ratio times -1, we will get -0.5. And for second part, we will get -0.8 because we clipped. And then the bigger number, the maximum is -0.5. So this means that we will give less of a punishment, less. So this is we will give less of a punishment to the models, because we don't want to give too big of a punishment anymore, because the model already made the bad token less likely. Let's see example with a positive ratio. So in this case, the new model thinks this token is more likely, increased the probability of this token compared to the old model, but it still gave the wrong answer. So here we will have, let's say, ratio is 2 and advantage is -1. So in the first term here, where we multiply them, we will get -2. And in the second term, where we clip this ratio to be just -1, we clip this ratio from 2 to 1.2 in this second term. And then we multiply the clipped ratio with the advantage. So we will get here, we want to get maximum number between -2 and -1.2, which is the clipped version. So this will be our final reward, -1.2. And this is now a bit counterintuitive to all of the previous examples, because here the intuition would be that we want to punish the model for making the wrong token more likely. So why does PPO not punish model here so much for making the wrong token more likely? I'm not sure, but this could be because we just don't want too big updates like this. We want to clip the updates. We want to reduce we don't want like too severe updates that could mess the whole model. That's my understanding. That will be it for this video. Join my school to become AI researcher. We have all of these classes and courses for free, and link below. It's free for now, but I'm gonna make it paid soon, so hurry up, link, and see you in the next video.